This is the first lecture for Chapter 4, and it is on multiple integration. In this case, we'll start with integrals that have constant limits. Recall from functions of a single variable that the integration is a limit of the Riemann sums. And the Riemann sums are the sum of the areas of rectangles that approximate the function. In this case, we have some function of a single variable, we'll call that x. And we're going over this interval from a to b. This would be the x-axis here. And the Riemann sums are the sums of the areas of these rectangles. There's light blue ones and dark blue ones shown in this picture. It depends on where you take the endpoint. So the Riemann sum has a base here of what I'll call delta x, which in the limit becomes dx. And that's one dimension of the rectangle. The other is the value of the function taken at somewhere in this interval. And that gives you the rectangles, and in the limit that becomes the integral. For the double integrals, we're really looking at volumes instead of areas. So what we approximate the double integral, we approximate it as a box. Before it was a rectangle, now it's a box because we're in 2 dimensions. So what I'm talking about here is a function of 2 variables, x, y. The base of the box, the area at the base of the box, is delta x times delta y. Remember, before there was only one variable, so all you had was delta x. Now you have delta x times delta y. That gives you the base of a box, this. And then the height of the box is determined by the function, the value of the function taken somewhere in the box. You can have right-hand, left-hand limits, or some other choice for the function. And this is how the double integral is written. You have 2 variables instead of 1, so you have a dy and then a dx. Because remember, the base of the box was that area, delta y times delta x, to give the base, so that becomes dy times dx. Now, for the limits of integration, if dy is on the inside here, then its limits are in this integral here, this integral sign here, and the limits for the outside, the dx, are placed here. So these integrals are nested. So here's a picture of this situation. We're looking at the volume shown here. That yellow surface are the values of the function over 2 variables, we'll say x and y. The volume is approximated by the boxes. The base of the boxes is given by dx times dy, and the height of the box is the value of the function taken somewhere in that interval, in those intervals. This is for a double integral. And it would be written like this, integrating the So when you go to perform this integration, what you do is evaluate the inside integral first, assuming that the other variable is constant. After that, then you evaluate the outside integral. It's important when you do these integrals to keep your work organized and not do any side calculation within the integral or within the equal sign. Otherwise, you will make a lot of errors very quickly. So here's an example which is worth a whole bunch of words. We have some function here, and in this case the function is e to the minus y times the cosine of x. And we're going to integrate it over the region y varying from 3 to 5. Here's the dy, that's the inside integral. And then the x limits are pi over 3 to pi over 2. So we start on the inside of this nested integral, And the first thing we do is integrate with respect to y, assuming the x is constant. Now sometimes you'll see people take that cosine of x because you can do it and move it outside that integral, and it's okay to do it, but the fewer things you do, the fewer mistakes you make. That's my philosophy. Okay, so it's better, I think, to just leave everything together. Cosine x is just a constant. It could be the number 12. Just leave it there and integrate with respect to y. So e to the minus y is negative e to the minus y, and the cosine of x is just along because it's a constant. And then you evaluate between y equal 3 and y equal 5 because those are the limits of integration for the y. When you're done with that, you will have a term in this case that solely depends on it's just a constant, and it's obvious that it's a constant. Then it's okay to move it outside the integral. You're left now with a single integral with respect to x, and you know how to do that, so you just carry out that integration and you get sine x, evaluate it between its endpoints, and this is the answer for that problem. Here's an example for a triple integral. Now we have three variables. We're talking about here is some function of x, y, and z. And you see the integrals here. Here's the dz. This is the limits for the dz. Now you have a dy, and the limits for y are 3 to 4. And then you have dx, and the limits for dx are on the most outside integral sign. So starting on the inside, you integrate with respect to z. X squared and y cubed are considered to be constants. Again, you could move them out, and some authors will do that. I generally leave everything alone. So integrating with respect to z by the power rule, that becomes z to the 5th over 5. Evaluate that at its endpoints. That is a constant. It's independent of everything, and you can move that outside. Now you have a double integral like you had before. So again, you have the dy in this double integral. Its limits are 3 to 4. And then on the outside, you have dx, and its limits are 1 to 2, written in the outside integral sign. So the first thing you do is take the integral of the y, the innermost integral there. So y cubed by the power law becomes y to the 4th over 4, and you evaluate it at its limits, y equal 3 and y equal 4. That gives you another constant which you can move outside the integral. You don't have to, but you can move it out. That is easier in that case. And then you're just left with this integral with respect to x. You might have noticed that sometimes the integrals were written dy dx, and other times the order was dx dy. Does it matter? It doesn't matter as long as the function is continuous in that region of integration. This is Fubini's theorem. So as long as the function, that would be your f of x and y, or in triple integral it would be f of x, y, z. As long as the function is continuous, you can change the order of integration. And sometimes it's much easier to do the integration in one way than in another. For the functions that I have shown here, it wouldn't have mattered. It would have been just as easy to do them in any other order. But sometimes it does make a difference. And here's what we mean by any other order. Here we have, well, I thought I had the marker. So here we have dy on the inside and dx on the outside. Now if I want to integrate with respect to x first, then I have to move the limits here, and I have to put the x on the inside. And then the y is on the outside. Same thing for triple integrals. The order shown here is z first, dz, dy, dx. In this case, you would integrate first with respect to z. Once that was done, then you'd integrate with respect to y, then you'd integrate with respect to x. And the limits are written in that order out here, with the z on the most inside one, and then y, and then x on the outside. Now if you want to integrate in a different order, with respect to y first, then I would have had to put the limits for y, which in this case is cd. I would have to put those on the inside to match up with dy being on the inside. We're going to compute now the average value of a function. And it depends on whether it's a double or triple integral, how you do this. If you want the average value for double integral, you take the integral as you did previously, and then you divide by the area. For triple integrals, you divide by the volume. And the area and the volume, the area is just the integral of dx dy over the same region that you took this integral of the function over, but you don't include the function with it. You just go dx by dy. For the volume, it's the same thing, dx dy dz, but this is not included. That gives you your volume. You use the same limits of integration for both of these. Here's an example of computing the average value for a double integral. So what we're doing here is we're going to integrate the function. Then we're going to divide by the area. So we're starting here with the integral of the function. Y is varying from -2 to 5. X is varying from 4 to 10. So taking the inside integral first, that is the integral with respect to y, we have just a y, and by the power rule that becomes y squared over 2, evaluate it at its endpoints, and get 21 over 2, which I placed on the outside. Then we're left with the integral with respect to x, which can be evaluated. That becomes x cubed over 3. Evaluate that at its endpoints of 4 and 10, and we get this value for the integral of the function. That's for the numerator. For the denominator, we perform the same integration without the function, without the x squared y in it, but we integrate, as you can see, over the same limits. Y is varying from -2 to 5. Y is varying from -2 to 5, and x is varying from 4 to 10. There is no function here. You simply carry out this integral, and this will give you that the area. And the area is 42, so you divide. That becomes the denominator. You divide by 42, and the average value of the function is 78.